ja ho sabeu. Avui tenim en Frédéric Cyr, de Fisheries and Oceans Canada. Ell va fer la tesi a la Universitat de Quebec en turbulència i després va fer un postdoc a Marsella en turbulència també i amb gliders, per això ens coneixem ja des de fa uns quants anys. I de fet ell ara ha estat fent una estada aquí amb nosaltres des del mes de setembre, si no m'equivoco, i ara ja està a les últimes setmanes abans de marxar. Pràcticament just després de Nadal se'n va, però tot el temps aquest que ha estat aquí l'hem aprofitat per fer coses en comú i per continuar treballant. A banda d'això, sé tu, no?
Good morning, everyone. Thank you, Jordi, for the introduction. So, as Jordi mentioned, I'm here during a research stay for 4 months, but and what I've been working on these last months is not what I will present today. I present something that comes from Canada, something I've been. Yeah, sure. It's better like that. So yeah, so what I will present today is more something that I've been working before coming here. I'm working on a similar topic since I've been here for these few months, but in the Mediterranean. So my talk is about climate and fisheries, so Decadal-scale bottom-up control in the Northwest Atlantic. My name is here, but it's really like a team effort. So all my colleagues here are from the same institute. We've been working on that for a few years now. And I would like to dissect a little bit the title. So there's the word climate and the word bottom-up in the title. So I will define them first. So climate, you may know what is climate, but it's a description of the average weather or in the case of the ocean conditions of a particular region for a certain time period, usually taken over a 30-year period. And I would like to distinguish between natural climate variability and anthropogenic climate change. The natural climate variability is something that occurs at multiple time scales, from interannual, you might know descriptors such as NAO or the El Nino Southern Oscillation, to much longer time scale, glacial, interglacial cycles. Anthropogenic climate change is really what we usually refer to when we talk about climate change. It's related to, of course, the human-driven imbalance of the Earth carbon cycle by putting CO2 in the atmosphere. In the case of this talk, I really focus on the natural climate variability of an ecosystem. And so, as Jordi mentioned, I'm a physicist, so I take the time to define the difference between bottom-up and top-down. Bottom-up refers to a trophic chain that is resource-driven, so limited by biotic or abiotic factors such as physical and biogeochemical environment, primary, secondary production, etc. Top-down refers to a trophic change that is consumer-driven, for example, where predator-prey interactions is as a leading order. In the case of this talk, of course, I will talk about bottom-up, because this is what is my title. Right, so here's my outline, a little bit of background, then I will just describe a basic functioning of the Northwest Atlantic Ocean, then talk really about Newfoundland and Labrador climate, where I work, and I will dig into the nuts and bolts of the bottom-up control on the Newfoundland and Labrador ecosystem. So some background. There's more than 500 years of fisheries in Newfoundland and Labrador. As you can see here, this is a map from the 17th century, where you have a Newfoundland here, and this thing here are the Grand Banks of Newfoundland. And from the 17th century, how busy was this place in history. So for hundreds of years, European mostly came and fish in the Grand Banks. And this until today. There's again a reconstruction here of landings, so cod landings in Atlantic Canada, reconstructed here. So we see for the last 500 years an increase and a dramatic decline at the end. So if we focus on that most recent period here, we see that from the early 1900s, pretty flat landings, and then a dramatic increase in the 60s, driven by the mechanization of the fleet, peaking in 1968, and then two decline. The first one in the early 70s, kind of a rebound, and in the early 90s, bam, no fish anymore. And so in 1991, there was basically no fish in the water, and in 1992, a moratorium was put in place, and is still in place today, 30 years later. Turns out that the 90s, early 90s, were the coldest period on record. So yes, there was overfishing, but also it was a very specific environmental period at the time. So this led to a lot of debates, and a working group was put in place at Fisheries and Oceans Canada, where I work right now, to put in place a monitoring program. So that's the founding document of that Atlantic Zone Monitoring Program, or AZMP, that was formally established in 1998. And in the very first paragraph of that document, the rationale for the monitoring program is there. So changes in climate cannot be ignored as an explanation for fluctuation of marine resources. So fast forward 25 years later, here I am, and I work mostly, a large part of my work is associated with the Atlantic Zone Monitoring Program. So all these red lines here represent sections that we go ship, seagoing sections where we collect physical and biogeochemical information. Some of these sections are sampled up to 3 times a year. So I work for the Newfoundland and Labrador region here. Some people work on the Scotian Shelf and other people in the Gulf of St. Lawrence. And we gather every year and we produce a report. Well, each of us produce separate reports for all the regions, but together we report on the oceanographic conditions in the Atlantic zone, in this case in 2019, but we do that every year. And this is used to inform many things about climate change, but also the fisheries. So that was my context. Now, a little bit of the basic functioning of the Northwest Atlantic. Just a parenthesis, so this is the Atlantic Canada. My workplace, usual workplace, is just here in St. John's, Newfoundland and Labrador, and I grew up on this small island there in Atlantic Canada, which is part of Quebec. But that's not the point of that slide, is just to show that this region is naturally highly variable. You can see here the map itself is the sea surface temperature at the warmest time of the year, so late August. And even the warmest time of the year, there's still freezing water flowing from the Hudson Strait, from the Arctic, flowing along the Labrador coast here. If you look at the color bar, this is close to 0 degrees Celsius. And this water meets the Gulf Stream and the North Atlantic current water, which is close to 30 degrees Celsius in a very short distance. So there's a huge temperature gradient in just a few hundred kilometers, huge temperature gradient, and that corresponds to where are the Grand Banks of Newfoundland, which makes it a so productive region. So this circulation here with the Labrador Current and the North Atlantic Current is part of a bigger picture that is called the subpolar gyre. So as I mentioned, Labrador Current, the North Atlantic Current, and then there's a return flow here, the Erminger Current, and then the East and West Greenland Current. So that subpolar gyre really distribute heat and all kind of biogeochemical tracer across the North Atlantic. And the subpolar gyre is partly set into motion by the mean wind pattern above the North Atlantic. So this slide here represents the sea level pressure, so the atmospheric pressure at sea level. On average, there's a high pressure located here near the Azores, a low pressure near Iceland, and this sea level pressure difference drives the mean winds above the North Atlantic. This is why basically it's faster to fly from Canada to Europe than coming back. The thing is that this sea level pressure pattern changes on decadal time scales. And I gave an example here. Instead of looking at the sea level pressure itself, we look at the anomaly. So how just a few millibar higher or lower than the long-term average. And there are decades, for example, here in the 60s, where the low pressure is a bit higher, the high pressure a bit lower, and other decades where the low pressure is lower, high pressure is higher. So the wind flow or the air circulation stronger in this case and weaker in the other case. And for our region on our side of the Atlantic, that would lead to colder weather in this case because we have a lot of airflow from the Arctic flowing towards our region. And this is usually described as the North Atlantic Oscillation, which is defined as exactly the sea level pressure difference between the high and the low pressure. So positive NAO for us is colder weather. But the important part here is that, again, as I said, since the subpolar gyre is set in motion by these mean wind pattern, a positive NAO, or in the case we have a lower low pressure here, leads to an inflated subpolar gyre with the Labrador current here being mostly diverted towards the east. And in the case of a weak subpolar gyre, the Labrador current just loop around the Grand Banks here a bit more easily. And this is the large scale. This has an influence on the regional scale. And I highlight this by looking at a temperature section from Seal Island. So this is here in southern Labrador. This is one of our key monitoring sections that we have. And I chose it because it highlights the cold intermediate layer, which is a key water mass for our region. So what we have here is, again, this is the shelf, and this is the deep ocean here, 0 to 300 kilometers offshore, and this is 0 to 500 meter deep. And this black line here represents 0 degrees Celsius. So everything within that black line is below 0, and this is the average, 30-year average of temperature in the middle of summer, right? So middle of the summer, we have this huge water mass below 0 degrees Celsius. And it occupies most of the volume of the shelf, right? The thing is that depending on if we are in this setup or this setup, this water mass has a tendency to change a little bit. And I give two extreme examples, I admit, 60s and the 90s. 60s, that CIL is just in small pieces, with the bottom temperature here being 2 to 4 degrees Celsius. In the 90s, the CIL was huge and was sitting on the seafloor. These darker shades of blue here is minus 1 degree Celsius. So basically the entire seafloor was filled with water below -1. Just as a reference, the seawater freezes at about -1.8. So pretty cold water. And that corresponds to the year where the fishery collapsed, right? All right, so that's kind of the context. I'll follow up on this later. Now, talking about the more regional climate, I'd like to bring another definitions right now, which is the notion of a climatology. So we define normal as a 30-year average over 1991-2020. Using that, we can define a standardized anomaly. So if X here is any variables, can be water temperature, air temperature, wind speed, salinity, whatever. If I take X and I subtract the average of X over that climatological period, I get the anomaly. So that will tell me that year is so many degrees Celsius above or below average. And if I divide my anomaly by a standard deviation over the same period, I get a standardized anomaly. So that would tell me this year is so many standard deviation above or below average. This is handy because standardized anomaly is unitless, so we can compare different variables with different units together. And we've done that with a colleague of mine to develop a climate index that can be used to inform fisheries management. So this index, so how to interpret it, so this is a time series, so from 1950 to present, so more than 70 years of data. All these, we have a list of 10 sub-indices here: winter NAO, air temperature, sea ice, icebergs, sea surface temperature on the shelf, temperature, salinity, and cold intermediate layer at this station 27 located here, which is one of the longest hydrographic times here in Canada. Bottom temperature on the shelf as well, and the area of the cold intermediate layer that I showed before on the sections. So they're all standardized anomaly that we see here, all color-coded. Darker shades of blue means colder, and darker shades of red means warmer. So we have basically a picture of the last 7 years plus of data here, and we can collapse that into a stack bar plot where we can actually see the fluctuation of the climate over the recent years. And finally, well, the index is just put at the bottom here as an average value. Okay, so I take my climate index. Oh, sorry. Yeah, so just a quick look at this climate index. There's a strong decadal variability. What is interesting for me there is that it's not a noisy signal. There's really like periods you can see where the index is mostly positive and then mostly negative. The mid-80s, early 90s, as I mentioned before, was the coldest decade in 70 years. You know, a lot of blue here, and you can see it all negative here. The 60s and the mid-2000s were the warmest decades, as you can see here and here. There was a recent cooler period, 2014, 2017, as you can see here between these two warmer periods. And then there's a developing warm period since about 2020 or 2018. All right, so now you know a little bit more about what's going on here. I will dig into really the nuts and bolts of my presentation about the Decadal-scale bottom-up control on the Newfoundland and Labrador ecosystem. So we take that climate index that I just presented. We apply a cumulative sum on the value of that index. So basically, it's just every point on the pink curve here is just a sum of everything that comes before. I do that in order to highlight the local maximum and minimum. So basically, when the sign of this index is positive, it increases, and when the index changes to negative value, then this cumulative sum starts to decline. And I really use that to separate some region of, you know, mostly positive, mostly negative of that climate index. And it turns out that if we look at that, this corresponds to known changes in the fisheries as well. As I mentioned, the 60s were the period where there was the biggest catch. Yes, it was due to the mechanization of the fleet, but also because of a specifically good condition for the productivity of the ecosystem, with the largest landing in '68. And then there was a first partial collapse of the fishery in the early '70s due to overfishing, but it also coincided with a period where the climate kind of switched from being like very like warmer and then suddenly a bit colder. And then there was a partial recovery that was partially explained by the introduction of the 200-mile limit economic exclusive zone. So basically, the Spanish cannot come fish in Canada anymore in coastal water, but not just because of that, because there was also an improvement of the climate and the productivity of the ecosystem. And then in the late 80s, successive collapse of both commercial but also non-commercial fisheries, not fisheries but stocks. So even non-commercial stocks collapsed in the early 90s and late 80s. And that led to the introduction of the moratorium here in 1991. And then following the collapse, that was kind of a dramatic moment for Newfoundland and Labrador. Like 40,000 people lost their job from one day to the next. It's about 10% of the population. There was some period of modest improvement of the stocks afterward. Even that in 2015, there was paper talking about the cod making a comeback in Canada. Unfortunately, the recovery stalled in about the time, 2015, 2016, 2017. And then since then, it seems that there's a kind of a recovery that is, again, continuing. But as I said, we're still under moratorium more than 30 years later. All right, so we take this picture of basically qualitatively put in green when the stock is doing good and in red when it's not doing good. And I put some nicknames with, largest landing, partial collapse, etc. And I kind of explode this picture in different periods. So that would be the record catch of the 60s. The dates are here. Then we go to the partial collapse in the 70s. The dates are here. Partial recovery, so you have to read it from left to right. Partial recovery in the late 70s. The collapse, modest improvement, and the stall recovery. And if we look, so again, this black curve here is the cumulative sum of the climate index. It's just climate, there's no fishery there. If we look at the sea level pressure anomaly during this different period, it's all blue, blue, blue here when the stock is not going good, and red above the pole when it seems to be doing better. So it seems that the environment somehow exerts a certain control on the ecosystem. We're going to try to dig further into this, because at the moment the link between the environment and the fisheries is mostly qualitative. Now I'll try to quantify this. But to do so, I have to focus on the most recent period, because we don't have much information except the landing since like before the 70s. So I will, and this is where all my colleagues come into play now. We look at different metrics that we can extract from the fishery. The first one is the groundfish, the trends in the groundfish biomass. So in pink here, you have the cumulative climate index that I already mentioned, with the dashed line separating the different period where I have different nicknames: partial recovery, collapse, modest improvement, etc. And in orange here, it's the process error of a groundfish multi-species surplus production model that attempts to account for changes in biomass caused by density-dependent effect and subtraction by fisheries. In other words, this curve is the variance that is not explained by density-dependent effect of the stock and by the removal from the fisheries. So it must be internal factor that explain these fluctuations. For example, changes in the climate. So if I look at this curve, again, and I separate for my different period, and I just draw a plain linear fit during the different period, I see, increasing, decreasing, increasing, decreasing. That's what I'm interested in right now. And I take the number of that slope and I put it on my figure here. So same figure as before. Now I have my little card here. And I have in green when there's an improvement, and in red where there's a decline. And the unit here is kiloton per year. So the slope of that linear fit. All right, and so it fits. In this period I have an increase, these two periods I have a decrease. I continue. I take multi-species biomass trend. So this is the scientific survey that we do since the 80s. And it's all biomass density of all species, so in ton per square kilometers. Again, there's a decrease here, kind of an increase, decrease. Take the slope, put the slope on the map. So I have my little ship here with the slope. Do that also for capelin. Capelin is our key pelagic stock, and this is estimated from acoustic surveys. So time series getting shorter now, but there's a decline in the 90s, of course. There's a modest improvement here, and a clear, like a short but intense decline when the recovery stalled. So I put that on my map again. I have my little fish, and then I have the trends here. So pretty cool so far. I have a link between large-scale forcing, regional climate, and the tendency in some stocks. I continue and I look at the primary production level. This time I had to go to a global biogeochemistry hindcast, so extracted from Copernicus. That's the product here, and I draw a box for the entire North Atlantic. The box is here, and I look at the primary production level. I cannot fit linear fit in this case, because primary production level, it doesn't make sense to accumulate from one year to the next. So I look at the level here compared to the long-term average, so low, high, and I do the same for secondary production, that is from our Atlantic Zone Monitoring Program. So basically the abundance of Calanus finmarchicus, which is our key copepod species. And again, I draw a different level like that, and I add them to the same figure, this time at the top here. So I have my primary production in milligram of carbon per cubic meter per day, and then same thing with the abundance of Calanus finmarchicus. And again, it fits. We have a positive value here when the climate seems to be in a productive state, and negative value when the climate seems to be in a negative or less productive state. So the question is why it works so well. So that's the next step. I'll give 3 hypotheses now. First one that I call the fish go away. So I've shown this figure before, difference between the 60s and the 90s. With, when the cold intermediate layer is so big, it can actually prevent the fish, it's too cold for the fish. This was brought forward in the 90s to explain part of the collapse. And again, there was a recent paper suggesting that also the mesopelagic fish and zooplankton can be affected by this. That's plausible, but it cannot really explain the changes in the primary production. The second hypothesis that I call the life is blown away, and it refers to this paper here that actually suggests that an inflated subpolar gyre blows life towards the northeast Atlantic. Remember, we are in the northwest Atlantic. Now, if it blows life to the northeast, towards Europe, towards Scandinavia, it might not be good for us. And actually, this is possible also because a weak subpolar gyre, which is more productive for our region, the Labrador current here seems to be looping better around the Grand Banks, and when there's an inflated subpolar gyre, the Labrador current is kind of diverted towards the center of the gyre. So another possible explanation. Third hypothesis, which is my favorite, is that there might be a mismatch between the primary and the secondary production here. So this is a recent paper that we work with colleagues. So just a quote from this paper: it is found that over interannual cycles, the ocean climate is significantly correlated with the timing of the bloom and the abundance of Calanus finmarchicus, which is a key zooplankton species for the ecosystem. And this is shown in these figures. So in blue, we have the climate index that I presented before, and in green, the timing of the bloom. So they are completely anti-correlated. So a warm climate means an early bloom, and a warm climate in blue here versus the orange curve, warm climate means more Calanus finmarchicus. So warm climate, early bloom, more Calanus. Why? The hypothesis is that the years with warmer climate lead to an early bloom, which in turn leads to a better match with the emergence of Calanus finmarchicus from diapause. So Calanus finmarchicus, they spend winter at depth in some kind of hibernation. And they come to surface in the spring, and they hope to find a bloom there. So if they come to the surface and there's no food, they might start eating each other and starving. So it was shown that an early bloom in our region leads to a better match with the emergence of that species from them. So that's the 3 hypotheses, and it's also the end of my talk. So in summary, so the Newfoundland Labrador Shelf and the Northwest Atlantic undergo large Decadal-scale climate variability. There are different phases that can be identified by looking at a relatively simple climate index. These phases are associated with periods of improvement and decline of the ecosystem productivity everywhere from primary to secondary production to pelagics and groundfish. There are periods of improvement that are linked to extended period of a warmer climate in our region, noting that we live in a pretty cold environment. The warmer periods are caused by a positive sea level pressure anomaly above the pole and potentially associated with a slowdown of the subpolar gyre. The warmer climate periods are associated with potentially more habitat availability for fish and zooplankton. This is the fish go away hypothesis that I mentioned. Warmer climate are also associated with an early bloom and higher abundance of Calanus finmarchicus, whether it's caused by a better mismatch or more retention on the shelf because of the Labrador current is staying close to the shore. Since 2018, the ecosystem seems to have entered a more productive phase. And finally, this is the key takeaway, the recognition of these different phases may help inform fisheries management. And this is really where I would like to go from now on, and what I'm trying to push forward in Canada as well, is how to take this knowledge and incorporate this into fisheries management. The recognition of that, the fact that there are some phases where the ecosystem seems more or less productive, can we take this into account? For example, in the 90s, where the collapse happened, we could have known 10 years before there was something going on with the ecosystem. It was pretty cold. If we had been monitoring this quite carefully, we could have maybe detected the changes before it affected the fishery. So this is the kind of idea that I would like to push forward as a researcher in the next year. But this is ongoing work, so I'll have to have another invitation to come back. So that's it. Thank you very much. Thank you, Jordi, Yves as well, for invitation to ICM, and everybody with who I interacted with during the visit. And yeah, I'm happy to take some questions or comment.
Preguntes?
Hello, thanks for your talk. I have a question because we are talking on a decadal-scale, no? And then about the catches, they start in age 4 or 5 or 3. I mean, the catch composition has a delay, no? Regarding the observations.
Yep.
And this can be, I don't know, the recruitment age, which do you know?
Pardon?
The age of recruitment to the fishery.
Yeah.
It can be 4 years or something like that?
Yeah, depending on the species, yeah. Capelin would be much faster. A cod, of course, it's
Meaning that this delay should be taken into account, no?
Yeah, at the moment.
When you merge the
it's
observation with the catches.
It's totally a valid comment. We kind of thought about that a little bit. The thing is that, you know, there's always some lag, some species lag, you know.
Well, lag, yeah.
But then we decided to go, instead of looking at year by year or lagging 2 years, we just look at period, like chunk of time, and this is why we're having like a 10 years or a 15-year period. We can kind of, you know, all these fluctuations are kind of smoothed down because we just look at, hey, what happened during this 15 years period? Is it getting better or worse in this 15-year block? So we kind of smooth a little bit the effect of the lag between the changes in the ecosystem, because also when the changes happen, it doesn't happen all at the same time. There's some metrics will start changing faster than others. It's just that when we kind of zoom out and look at what's going on at the more decadal scale, this is where we...
No, I agree.
Yeah.
It's fine, but maybe results would improve taking into account this lag.
Definitely. For example, we know, I didn't talk about that, but I have with another colleagues, we discussed snow crab. Snow crab has a 7-year, well, even more, like minimum 7 to 10 years lag with the NAO, for example. Yeah. Because why? A crab entered the fishery at that age, at 7 or 10 years, and cold years is good for snow crab because it creates a cold environment that protects them from predators. So there's a good recruitment in colder years, but these crab will enter the fishery 10 years later. So this is an example where a lag we've shown that it works pretty well, actually.
Okay, thanks.
Yeah.
Més preguntes?
Hi, thanks for the talk. The graph that you show the catches from cod, which is a very impressive one with the increases and the crash, and now it's really, you don't have data because there is a moratorium.
Well, actually, there is data. It's just that it's so small that we don't see them.
Okay, but the graph is catches, no? If there is moratorium, there is no catches. Or what is the graph exactly?
There's a moratorium in the coastal water, but there is what they call a sentinel fishery or stewardship fishery. So there's a little quota that is used to monitor the catch. Outside the 200-mile exclusive economic zone, there are a European vessel coming to Flemish Cap, for example, tail of the Grand Banks, and there's a small quota that is managed by NAFO, and yeah, there is a little bit of fishery there.
So then the graph that you show, it's the reality. It's not because the moratorium, but this is...
No, it's the reality, yeah. That's what...
which is impressive.
There is some data, but it's so small that we can't see.
I have seen the data, yeah.
Thank you very much. It has been a very, very interesting and well-structured talk. I like it. And it's highlighting one point, which is the importance of having a good monitoring of all, and a long time monitoring of many, many data that has been typically ignored in many other countries, like unfortunately this one. Then, just a technical question.
Yeah.
When you talk about the production model, multi-specific production model in one of these
this one?
Yes, the process. Okay, this one. What is this production model? The surplus production model is based on catches. Is based on catches, annual catches of several species that are pulled, or what kind of treatment have you done to this model?
The specific of the model itself, I'm sure my colleague here would answer better, but it's there's multiple, all groundfish fisheries, cod, plaice, flounder.
You pulled all this information to produce your model.
Yeah, it's
your production, your surplus production model.
Exactly. The model itself, recreate the catches, but the process error of the model has a fluctuation.
Mm-hmm, yes.
Right, and this is the process error that I show here.
Yes, no, I was referring to the model.
Yeah, the model itself. Yeah.
Okay.
And
the pool of catches.
Yes, all catches. There's I'm not sure, there's like 10, 12 species altogether that are pool, and it's the average biomass here.
Thank you very much.
Alguna altra pregunta? No? Well, thank you very much. I fins la propera.
Regardez ça. C'est ça. Je l'ai...